Great. So it's just a very impressive lineup of speakers today. I'd like to introduce a friend of mine, Alex Spengler. I feel like when I first met you, Alex, I was very just impressed that I knew someone who was designing a web app. I don't know very many people who do that. But he just pulled out his phone and showed me this amazing like orthomosaic of a reef. And he's like, oh yeah, I made that. And I was very astounded. So he's going to share some of his master's thesis work with you. It's entitled Mapping a Reef in Minutes, Comparative Analysis of Underwater Photogrammetry Systems for Accurate, Affordable, and Rapid Data Collection in Threatened Coral Reef Ecosystems. So would you please join me in welcoming Alex Spengler?
Thank you, that's very nice. I'm Alex Spengler. I'm a graduate student here, at UH Hilo in the TCBES program and a researcher in the Mega Lab. Coral reefs. Coral reefs are important for a number of reasons. There's this anecdote that gets thrown around all the time. It's like 1% of the ocean floor houses 25% of the marine diversity. That's coral reefs. They provide nurseries for juvenile fish to grow up and a wealth of habitat space for invertebrates. They're also important for communities for a number of reasons. They create awesome wave breaks and support community involvement in the ocean and reef ecosystems. Those nurseries create fisheries or support fisheries which support economies and feed people. They're also important for the defense that they provide. They act as a natural wave break for wave energy, storm surges, prevent flooding and erosion, in addition to providing insight into these ecosystems that are relatively hard to survey. They kind of act as a canary in the coal mine. The corals bleach, and that bleaching kind of can clue us into different stressors in these ecosystems. Coral reef science, a lot of it's done using a technique called photogrammetry, or structure for motion photogrammetry. And that's a fancy word for taking a bunch of pictures and stitching them together, making a big panoramic image. Usually that's done with a diver and a big DSLR camera. That technique looks something like this, where a diver kind of swims in a zigzag pattern, collecting a bunch of images. Usually those images have a lot of overlap, so like 60 to 80% overlap between those images. And those images are brought into software that uses this cool technique with the sequential images. You can generate 3D models just from 2D images. And the way it works is kind of similar to the way that our stereo vision works, in that we have two little cameras here, and our brain is doing a lot of processing in the background to figure out how far things away are. And the software kind of does the same thing, where it's matching coral or rock in sequential images and getting them from different perspectives, and we're left with a 3D model. Scientists and researchers export like orthomosaics, big reef snapshots, and a digital elevation model from those 3D models. With those orthomosaics, researchers can go in and trace out, that's kind of where like the red, the yellow, the blue there, what I'm trying to communicate there is researchers go in and ID corals based on species, size, or health condition. And that can give us insights into community composition, what species are where, how big they are. We can visit the same place year after year and see how things are changing. And we can do similar stuff with the digital elevation model, where you can kind of put down a virtual rugosity tape and figure out how much slope or structural complexity is in an area. And that can give us insights into benthic structure. And so those look like this. So on the left is an orthomosaic. You can see all the colors there, a bunch of corals, different structure. And in the middle is an example of a real digital elevation model, where you can see kind of how close things are to the viewer, how far away they are. The white things or the lighter colors closer to you, black further away. And then on the far right is kind of the end product, right before like the data gets analyzed, where a researcher went in and literally traced every single coral and ID'd them, thousands of corals, and sized them. And that gives us super valuable insight into our reefs. And this is all possible thanks to the almighty camera sensor. So there are a bunch of devices that use CMOS sensors, going from like a fancy full frame camera to an iPhone. They all have these imaging sensors. And over the last 10 years, these imaging sensors have gotten smaller, but also have gotten a lot more powerful. They can produce higher resolution images. And in the remote sensing world, the metric that we use, kind of analogous to resolution, is ground sampling distance, or GSD. So on the far left, there's kind of like a pixelated orthomosaic, and that's like a lower resolution. I think it's 1 centimeter, roughly, resolution. And to the right of that, it's a higher resolution, 1 millimeter. So for every pixel, it's like a millimeter. And GSD is a product of 4 things. So like image size. So in video, that could be like a 4K video versus a 720p video. The physical size of your sensor, the focal length, and the distance away from your subject. So if you have a really fancy camera, you can be further away from your subject and get the same results as someone with a lesser camera that's really close to their subject. And that's all kind of going into what I'm exploring here. I'm curious about the breakpoint between these 2 different camera systems. So I'm using 2 camera systems that are readily available and used by organizations and individuals. And I'm curious into how those differ. And I'm investigating the photogrammetry products of the 2 platforms and kind of comparing those. So I have this rig here that's basically just a GoPro on top of a DSLR. I'm using a Canon 60D and a GoPro Hero 4. These are both pretty dated systems. They're both around 10 years old, but they're being used. Like there's papers that are published using orthomosaics from the 60D. And the GoPro, a lot of people have GoPros, a lot of community members, people that are into ocean sports. GoPros are available. And the GoPro is a lot smaller physically, but also has a teeny tiny focal length, tiny images, tiny sensor. It's also a lot cheaper. So just before I did anything, just looking at, before I got in the water or anything, data collection with a GoPro, I'd assume would be a little bit quicker. You can take video, kind of split the video into individual images instead of clicking the shutter with the DSLR. Processing, because you're using smaller images, the pipeline gets a little bit shorter, or quicker rather, but there's an extra processing to split up the video into images. And then I just assumed, as I'm sure most of you, that the quality of the GoPro would be, the end product produced by a GoPro would be lower than like a higher end system. And so the metrics I was using to compare were resolution, or GSD, point density, and that's point density per area. So in these 3D models, they're kind of like a big cloud of individual points. It's a cheaper way to, instead of building a 3D model and having a bunch of triangles, you can use like the vertexes of the triangles and have a cloud and kind of compare that. A higher resolution, or a more detailed rather 3D model, would have more points. And then reprojection error, so that's like when you use scale bars to basically define, to be able to measure stuff underwater, you need a comparative scale bar. And then having multiple scale bars throughout your survey area allows you to compare, to be like, hey, software, it's half a meter here. And then the software is maybe like, hey, this is bigger than a half a meter. That might be indicative of some error. And then finally, some point cloud comparison. So because the 2 camera systems are attached, you can do this cool thing where you can layer the point clouds on top of each other, like perfectly, and see where and how they differentiate. So initially, I went out to Mahu Kona and did some scuba diving, and I basically surveyed the same location, the same area, at 4 different depths. So 1 meter above the subject, 3, 6, and 9, and compared them. So this is just a snapshot of the extremes there, and it might be tough to see, but on the top left is like the GoPro at 9 meters, which is pretty tough to look at. It's hard to kind of resolve anything if you told an intern in the lab to be like, oh, I identify all the corals here. It'd be pretty tough. And that's part and parcel to the relatively low resolution. So this is about like 4.5 millimeters per pixel. In the remote sensing and photogrammetry world, that's usually pretty good, but they might be measuring whole forests with like a drone. This is pretty close to the subject still. And down below, the results are kind of comparable between the GoPro and the DSLR, still sub-centimeter when you're about 1 meter from your subject. Then I went to Lehala here in Hilo and hit it hard, did like 20 surveys all in this area. It's a really cool area in that it is like a shallow tide pool. It's really accessible, especially for snorkeling. And I collected 20,000 images, made 54 3D models, 27 pairs of those models. And I found some results that aren't all too surprising. So this is all kind of developing. I'm not done with my thesis yet, but the GoPro had a greater GSD or a greater, which is kind of backwards. You have to do it had a worse resolution. And that's kind of to be expected. For the point density, so how detailed those point clouds were, the 60D or that DSLR had a much greater point cloud density, so just a more detailed model. And then kind of following that trend, the GoPro had more error, so more error with the images. And the point cloud comparison looks something like this. I'm still kind of workshopping how to best communicate this. But for each survey instance, there are two models. And this is the kind of the product of laying two models on top of each other. And in the right, or on the left-hand side, is a little box and whisker plot. And it'll show you like the distribution of the distances between points for all these plots pictured here. And it's pretty small. So the units here, it's a little wonky. It's like all under 0.005 meters. So all under 5 millimeters. And that's pretty low when you're thinking about differences between two 3D models. So pretty good results from the GoPro early on. And there's some interesting trends that I've noticed using this M3C2 comparison. And that's illustrated here. It might be hard to pick up on at first, but down below is like a certainty value on the software kind of matching the two clouds and getting distances. And you see some red is lower certainty, green or blue is high certainty. And there's like a ring of red around the edges of the images. And when we look at the images that I showed you before up on the top of the cloud distances, there's oftentimes like a color around the edge and a little bit of color in the center. And I think that this is like an artifact from the GoPro. So the GoPro has a fisheye lens, which naturally flares out at the edges or skews the image at the edges. The processing software compensates for that a little bit, but it's still present in these models here. And that's something I'm currently kind of investigating. Why is this all important? Who cares? This dude took a bunch of pictures with a GoPro underwater and stuff. It's important for planning. So I want to build like a playbook for organizations, researchers, individuals to do science and participate in their community. So if you have X funds, or if you have, I don't know, a couple $100, it's probably not realistic to say, hey, you need a $10,000 camera to survey your reef if you want to engage in coral science. If you're limited to snorkeling and you can't get close to your subjects, you might fit here on the work chart or whatever, or the game plan. It also allows us to do really powerful citizen science. A lot of where citizen science kind of falters, in my opinion, is like the nuances of training individuals over the course of a day or hours and being like, hey, identify this species versus this species of corals or birds. And that can be tough, and oftentimes you have to compensate for that error. If the citizens are just objective observers and are just more or less a vehicle for data collection, potentially that the data that they're collecting is the same that a trained scientist would be collecting. And lastly, community engagement. It would be really popular, and there are some exciting things kind of going in the Mega Lab with bringing this kind of science to the public and to different communities that have been outside of science, like surf communities or skate communities, and having them do science in the shore breaks that they surf every day. I'd like to thank the Mega Lab and TCBES. Thank you. Questions?
Oh, so we have time for one question. So your hand up.
Make it count. Yeah.
So is the GoPro going to be in a high enough quality to say AI is going to classify? I know that using AI to correlate some of the tech.
Yeah. So the question that was asked was, could the GoPro create a product that's good enough for AI to identify corals? Yeah, it just depends on how close you are to your subject. So if you're 9 meters away, probably not. But if you're really close, the results are pretty comparable to a higher end camera system. Yeah, thank you.
Great. Oh, Alex. All righty.